All right, this is homework 3A, question 1. We will derive and explain the energy balance equation for flow systems, explaining why injection work per mass is equal to pressure over density. We can draw a simple pipe to see what a flow system might look like. Now, there will always be an in and an out. We can start by labeling our system's energy makeup with respect to its differential mass. So that's going to be our internal energy is U, plus our gravity times height is going to be our potential energy. And then lastly, we will have a kinetic energy, which is V squared over 2. We also know that this system makeup is going to be equal to the following. We'll have the same as we did over here, just with our differential mass going in, and then same energy, so we can just write that. And then we subtract what is going out of the system. So in terms of energy, we have this. And then we also need to take into account the system's heat. We need to take into account the system's work. And then we also need to take into account the injection flow going in and out of the system, which will be, I can write down here first. So we know that work is equal to force times distance. We know that pressure is a kind of force, and then we know that D can be rewritten as volume over area, and then volume over area can be rewritten as M over density. All right, so if we rewrite what we just discussed, we know that work is equal to pressure times mass over density. We divide both sides by mass. It can be seen that work per mass is equal to pressure over density. And that's our kind of how we come with injection work per, injection or the flow work per mass is equal to that as the problem stated. Again, this will be relative to our changing mass for in, and then our mass going out. All right, so a little bit messy because it's kind of a long equation. We can box this in and move on to the next question. All right, this is question 2 from homework 3 part A. We are given that the flow system is in steady state adiabatic conditions with no change in internal energy and no non-flow work. We will be deriving the Bernoulli equation from the energy balance equation that we derived from question 1. So I did go ahead and move that down here just to get started a little bit quicker. So from the problem statement, steady state, we can tell that our adiabatic conditions, steady state and adiabatic condition, is going to effectively cancel this and make our whole equation equal to 0. It's saying that what goes in is going to come out and they'll be equal. So now we are going to condense the things that happen in and out. So that's going to look like this. These guys don't change. You just get to rewrite them. That equals 0. Our next step is going to be moving this and this to the other side. So we do that to make it a little bit easier. dm u2 minus u1 plus h2 minus h1 times gravity plus v2 squared minus v1 squared divided by 2. And we get to do the same thing to this one, p2 minus p1 over density. It's all equal to what we left on the other side. All right, and then our next step is going to be getting rid of these on that side of the equation by dividing by dm. My next step is going to be turning these guys into another simplified version. So change in u plus change in h times gravity plus, we can't do that here because they're squared, but we rewrite, and change in pressure over density. And then from our, well, let me finish writing that before I keep working. All right, so what I was going to say is that from our problem statement, we can cancel a few things. So there's no change in internal energy, which means that we can get rid of our change in U and our change in Q. And then it also gives us that there's no non-flow work, so we can get rid of this as well. And that will give us our Bernoulli's equation, which is what we were asked to solve. So I'll rewrite as such, and this is our Bernoulli's equation. All right, this is question 3 of homework 3 part A. We're given a constant diameter pipe with no change in height and no heat flow. We will derive the change in temperature from our change in pressure with a pressure drop of 60 psi. So we want to find the change in temperature of water. So I listed some of the constants that we will be end up needing. So first we can draw a picture. Here's our pipe with no change in height and a constant diameter. We know that there's going to be a 60 psi drop, so we can start with our initial being 60 and our ending 0. So to relate pressure to temperature, we can do change in pressure over density is equal to negative CV times change in temp. From here, we should have everything that we need, so we can go ahead and plug our numbers in. 0 minus 60 over 10 to the third. And then we do have to convert, so using the conversion I have listed, we'll do this to get it to pascals, and then we can set it equal to negative 4185 times change in temperature. So dividing by negative 4085 makes this side end up being positive, and our change in temperature I did on the calculator. Oh, okay, well, I had done it on the calculator, but we can do it again. I'm when this is all going to be over. So if we write what we solved for over here, close that, we get that our change in temperature is equal to 0.1 Kelvin. All right. All right. Question 4. At fluid level H and hole size A, at bottom, use the Bernoulli equation to derive an expression for volumetric flow rate out of tank. So, like any other problem, we will start by drawing a picture. Here's our tank with fluid level at H. Here's our hole. We are going to make 0 at the bottom for H. And then from here we'll start by writing the Bernoulli equation. Bernoulli's equation, we know, is P2 minus P1 divided by 2 plus gravity times H2 minus H1 plus V2 squared minus V1 squared divided by 2 equals 0. All right. So if we think about our problem that we've just described, we know that we can start to eliminate some of these things. The initial velocity of the water is going to equal 0 because it starts from a steady point. It's not flowing yet. So we can effectively get rid of this variable. We can also know that pressure at the top is going to equal 0 because there's nothing happening, and then when the tank is empty, there's also nothing happening. So that one will also equal 0, eliminating this as well. And then from there, we know that we labeled H at the bottom as 0, therefore H2 will equal 0 and H1 will be at the top, making this a negative H. So we can rewrite a little bit after getting that out of the way. Negative GH will be the changing, a negative change in height in gravity, plus our V2 squared over 2 is equal to 0. So from here, we can just go through and solve for our volume, for our velocity. So we can move our GH to the other side. That'll give us GH, positive. And then we can multiply by 2. And then to get rid of this guy, we can do a simple square root. And then from here, we know that Q is equal to VA. So in terms of volumetric flow rate, now that we have V solved for, and we have area A given in problem A, our volumetric flow rate is going to be equal to radical 2GH times the area of the hole. And that should be it for problem 4.